Today's seminar is done by Sam Panno. He's a geochemist, got his undergraduate degree in geology at Oregon State, got his master's at SIU Carbondale, and for about 3 decades, right?
That's right.
3 decades. He has been with the Illinois State Geological Survey in Champaign. His interests are many, but some of them hit home to us. He's probably explored Southwest Illinois and the Karst Sinkhole plain more than any other researcher in the state. His particular interests are groundwater quality, the nature of karst, and he'll talk about it today. He's innovatively come up with the most creative method to date New Madrid earthquakes in our region. And you're going to explain the process? Okay, because it's a no-brainer once you think about it, but I would have been thinking about it forever. I'd never come up with it, so. Okay, any questions? He's going to do about an hour and a half, and then you can do questions afterwards, and we'll have time to talk, okay? Thank you. Sam.
Carl. Can all of you hear me? Way in the back? We have a sound system just in case. When I first came to the Geological Survey in the late 80s, I was asked to come down to Southwestern Illinois by Joan Beatty, who worked here at the health department, and they were having problems with well water contamination, and there were something like 2/3 of the wells throughout the area were contaminated with fecal coliform bacteria and other types of bacteria. So they were wondering why, and we came down initially and looked at that and looked at the karst and found a lot of things we could do research on. It's a unique area. When we go to areas in karst throughout the United States, this is one of the most intensely karstified areas. With the dissolved rock and passages through caves and a lot of sinkholes. And I'll talk to you a little bit about the geology of that. But what I want to do is go through the beginnings of Illinois, actually the universe, but that would be a very short thing. Has anybody seen Neil Tyson deGrasse Tyson's show on Cosmos? Yes. Okay, I haven't seen it either. But, I'm looking forward to it. So, but I did look on the internet, and I watched one of his interviews, and I thought, oh, this is great. I wish I could present like that, but unfortunately, I can't. But what I'll do is show you some of the research we've done in this area on the geology, the hydrogeology, the earthquake studies, and more recently we're looking at salt deposits, or not salt deposits, but salt springs throughout the Illinois Basin or Illinois, basically the same thing. And the springs have a history to them. They're high in sodium chloride, so the early pioneers, well, the Native Americans would use them for salt. The early pioneers used them, and then the people used them as spas and medicinal purposes, and some of them are still active as far as being spas. And there are a couple here in Monroe County. So I'll talk about those a little bit. Also, forgot to mention, I'm going to talk about something called LIDAR, elevation models. Does anybody know what LIDAR is? No. It's a technique, and I'll talk about it, using lasers, airborne lasers, and they basically, let's see, there's a laser on this, I think. So they go across the ground like that in low-flying planes, and the laser flashes bounce off the ground, come up to the plane, and they have GPS within the plane, and they could make topographic maps, actually models of the surface of the Earth, and you can see rocks this big in the LiDAR elevation models. So we can use that to look at how many sinkholes there are. And the nice thing about it is they go through trees. So the laser goes through trees and hits the ground, and at some point you can use a mathematical algorithm to remove the trees from your image, and you can see what the ground looks like. So things we couldn't see before are now we're able to see all over the state. Okay, we'll begin with this. I like space movies, and and space always seems to have music associated with it. So that was the Big Bang. It probably sounded very similar to that. Going back to the beginning of the universe, which I thought would be kind of fun, everything started out at an atomic level, very, very small point that exploded in a rush of photons being particles or waves of light. So basically, when they say let there be light, that's basically what you had, a big flash of light. And then minutes into that, there was matter and antimatter, which if you watch Star Trek, you know that when they combine, they explode and disappear. And so the universe was full of matter and antimatter, and somehow 1 out of a billion pieces of antimatter disappeared. Nobody knows why. And so that left 1 out of a billion pieces of matter, which now make up the universe. This cooled and became atomic particles within a couple of minutes. And then when things cool down to a few thousand degrees Kelvin, which is 4,000 degrees Fahrenheit, a very hot oven. I guess that'd be a really hot oven. But the protons, the positively charged particles, combine to form, with neutrons, to form hydrogen, helium, and a little lithium, but basically mostly hydrogen, which is consists of 1 proton, 1 neutron. And it's the simplest element we've got. And then about a billion years past that explosion, we started forming galaxies of dust and hydrogen. So all the matter began swirling around the vortex of maybe a black hole. I'm not sure why they did that, but the gravitational forces created galaxies. We'll talk about that in a minute. And then within these galaxies, which had a lot of hydrogen, we started forming stars. They became incubators of stars, and within the stars, the protons were actually forced together to form additional elements, hydrogen, helium, lithium, and so on, up to iron, which is like 26 protons. And the pressures were great enough to actually force these things together because they're positively charged and they're pushing each other apart. So you started forming all the elements up to iron, and that was it. The rest of the elements had to be created when there was an explosion, a supernova, and so the star collapsed and then exploded, creating all the other elements. So if you're wearing any jewelry with gold in it, it's from a supernova, literally. Let's see. So at some point, you get these stars forming, exploding, and pretty soon the entire universe is full of a lot of dust and particles and fragments of stars that have collapsed and exploded. And then you have the makings of a universe that we know today. And so this is some of the dust clouds, which are actually star nurseries. And the stars are forming in there. That what happens is the gravitational forces bring all of this material together, the hydrogen, the dust from previous stars, and creates additional stars. And interestingly, if you look at the universe as it is today, it's about 93 billion light years across in diameter, roughly spherical, and 14 billion years old. So within our galaxy, the Milky Way, we have about 100 billion stars, and we're right at the edge of the Milky Way on one of the spiral arms. What I find is really fascinating is that we're looking at the universe with the Hubble telescope now and other means, ultraviolet and infrared technologies that give us a lot more information than what visible light can give us. And we're only seeing 5% of all the matter in the universe, or all the material. So the other 95% is referred to as dark matter and dark energy. And nobody knows what that is. Nobody's seen it. We can't detect it. We know it's there because of gravitational forces and the way orbitals behave. So it's a huge mystery. So when somebody says, oh, well, here's what's going on, this is what happened, 3 minutes into the origin of the universe, blah, 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 it'll be revised, so so don't memorize that stuff. So this is one of the spiral galaxies. Sort of looks like Milky Way, and if it were, we'd be somewhere out there. Oops. Carl warned me about that. Said, don't touch the screen. Anyway, so there's stars forming in the gases and dust surrounding what is probably a black hole in the center. It seems a lot of the galaxies people have looked at have black holes in the center, which are huge, collapsing. Words escape me right now. But you're all familiar with black holes, I hope. Yes. Okay. Yeah, they're called a singularity, and it's from I think a collapsing star that created pushed all the matter into a very small package, so that things started collapsing into it, and even light, so it hence the name. But so we'll go into nucleosynthesis of the elements. This is the sun, could be any star, but these are the elements that form within the star, within the center, because the protons are all getting pushed together. So hydrogen has 1 proton, helium 2, lithium 3, barium 4, boron 5, carbon 6, and so on. So down to iron, and nothing else forms in that other than these elements, unless the thing explodes. So you get down to iron, which has like 26 protons in the nucleus, and if you look at the Crab Nebula, which is the remnants of a supernova, you see all the rest of the elements coming into play, and you're going past iron, which is here. So you form hydrogen, helium, lithium, and so on. So carbon and oxygen and nitrogen, these are all very important for life. And so you get those first 26, iron is in your blood. I mean, it's all the stuff that you need. And then you get the rest of the stuff from the supernova. And and you get things like arsenic, uranium, all the things you don't really want to be around, except gold, and that looks nice. So anyway, so those all form, and that's why heavy metals, for example, are not good for humans to interact with, because we're just not born into something like that. We're just not used to that. All right, so we form the stars, and then around the stars, we get this huge clump of gas and dust from previous stars exploding and fragments. And so this is our solar system. That's the sun in the middle, maybe. This is an early photograph of it. And then, not really. Then the materials start to rotate around this because of the high gravitational pull of the sun, and you may have a large clump that starts going through, and because of gravitational properties, it collects more stuff and gets bigger and bigger. And then as it gets bigger, it attracts more material. And so we get the planets forming. And so there's Earth forming about the third orbital from the sun. And basically you're sweeping up all this material. And in the meantime, there's chunks of stuff flying around, hitting all these things, breaking them apart, they recombine. And so it's rather chaotic. But at some point, Earth is formed. Sorry. It's my favorite piece of music. It sort of sounds like Earth. Anyway, so the Earth was formed, and as the Earth was forming, you probably wonder where the moon came from. Who knows where the moon came from? Right. Yes. So something the size of Mars came by the Earth as it was forming, and when these planets form, they're molten, and so all the heavy stuff, the iron, the nickel, the gold, everything goes to the center, because they're basically, it's like if you were melting something on a stove, all the heavy stuff would go to the bottom, the light stuff would go on top. So like silica would go on top, and then iron would be at the bottom. And so it's like a slag. And so the Earth was sitting there, and then this huge thing came along about the size of Mars, sideswiped it, and left a big gouge out of it. So all these fragments flew up, and so back in that day there was no collision insurance, so they didn't have it repaired. And not really. Anyway, so this stuff started orbiting the Earth, and eventually accreted into the moon. And one of the things that is fascinating is that the moon is only about 1% of the mass of the Earth, because it has no iron core like all the planets, most of the planets do. So it's very light. So when the first astronauts went there, they collected it. They collected samples from the moon, and found that it was the same material that was on Earth, and it was essentially material from Earth. And I think they used isotopes and rare earth elements, other things to determine that. And then, so we have the moon. Oh, sorry. The other thing that was really interesting is, if you notice, the moon has a lot of craters in it, and we don't see many craters on Earth, or many other planets. Maybe Mars has craters, but most of the planets have atmospheres, and we have some sort of weather. We have weather, and the craters are from early times when these planets were accreting and being bombarded by everything in the solar system. So this peppered look, it's is evidence that we were hit by all this debris. They were hit. The moon was hit by all this debris. All the planets. So things have quieted down. We're not getting hit by really big things lately. Not to say we won't. So life sprang up about 3 billion years ago. Can you read that? Okay. And then we've been looking for life on other planets, like Mars. Right, so I probably offended everybody with this. So jumping to the Mississippian period. So 3 billion years, life forms. And nobody knows how life formed. It may be something that is throughout the universe on many planets, but it's nothing we can prove, nothing we can look at this point. So we'll go right to the Mississippian period, which is like 350 million years ago. And so this is Illinois. Let's see. Right there, and we're right there in southwestern Illinois. And you'll notice we're underwater. This was a period when there were about 7 times during the formation of the continents when everything was underwater, almost everything. And the oceans came up, and they were fairly shallow seas, maybe 30, 40 feet, and tropical. So this is the equator. So the Illinois, or the United States, was down by the equator, and I think it goes right through this area. So that, and life in southwestern Illinois looks very different than it does today, with cephalopods and sponges, horned coral, a lot of things that precipitated calcium carbonate, calcite, which is most of the material we're sitting on in the bedrock. Excuse me. Okay, so we're sitting on bedrock made of calcium carbonate, and it's from millions, let's say, what was that? So it's about 55, 60 million years of materials deposited on the floor of the sea, which is a long time. So you can create a lot of material. And this is what the area looked like, southwestern Illinois looked like at the time, with probably little pieces of land sticking up, and shallow, clear seas, skies were beautiful. Today, it's kind of gray, but you can see the limestone here on the bluffs that was deposited by all those sea animals. And if you look closely at that, you'll see some of the fossils in there. Okay. There we go. All right. So we see those fossils, and so we know where this material comes from. And now I'm going to switch to a little bit on the geology of the area. And this is Illinois, southwestern Illinois, and there's a cross section through here. Basically, it's like you had a cake and you sliced it through and opened it up, and the rocks are exposed throughout, right across all of Illinois. And the Mississippian rocks are the carbonate rocks we're seeing in this area. And we're located here just below that B. So where this limestone is exposed is where it's coming up out of this basin. And then if you go to the east, you run into Pennsylvanian rock, which is shales and coals and that sort of thing. So we see that to the east. And then deeper, you see other things, mostly carbonate rocks, limestone. I can go with that. And one of the things about carbonate rocks or limestone is that it dissolves in rainwater and snowmelt, as well as soil water. So the calcium, the carbon dioxide in the atmosphere mixes with the water, forms carbonic acid, which is it's a very weak acid, but it's enough to migrate through fractures in the rock and dissolve the rock surfaces or the fracture surfaces. So this is a map of the karst areas of the Midwest, as made by the U.S. Geological Survey, and so they're looking at karst limestone and dolomite up here. But we're located here, and we have a lot of karst. And interestingly, it's the area we look at mostly is St. Louis limestone. And if you follow that, it goes down into Kentucky, where the Mammoth Cave area is. So Mammoth Cave is basically the same rocks that we're sitting on. So you form some really huge dissolved rooms and caves and a lot of sinkholes. So I wanted to define karst. And karst doesn't necessarily refer to sinkholes. I mean, you have sinkholes, and you usually do in karst, but it doesn't have to have sinkholes. It refers to, I'll read it, both the surface and subsurface, an area affected by conditions of the overlying bedrock, specifically surface topography and hydrogeology. So you can have groundwater flowing through fractures, large fractures in an area, and not have sinkholes. But sinkholes are certainly one of the hallmarks of karst, and we have them here in spades. This is a geologic map of southwestern Illinois, and there's some structures. These are folds where actually the rocks are actually folded a little bit. So, but the blue, I think it's blue, is Mississippian age carbonate rock, about 350 million year old rock from the seafloor, and then this is Pennsylvanian rock to the east and far east. And then so this is what's dissolving, and then this inset shows a little bit of the area that's karst, a lot of sinkholes. And so this is an aerial photograph of the sinkhole plain, and it's this area here is referred to as the sinkhole plain, and it includes part of St. Clair County, quite a bit of Monroe County, and a little bit of Randolph County. And so this is kind of a cutaway version of it, so you can see the surface sinkholes and then the crevices that create these sinkholes below, and I'll show you how they form in a minute. But what you have is an area that typically doesn't have surface streams. The streams are underground, and so you'll get sinkholes that actually act as drains to that aquifer, and it is an aquifer. And not all of the area is cavernous. The caves are discrete. They're fairly small when you look at the mass, the total body of rock, but most of it's fractures, and they're about a couple inches to 6 or more inches wide, and you can crawl into some of these things if you feel like it, but you don't go very far because but the water does, and it just goes through there. And that was the reason why anything that was dumped onto the surface, or, you know, for example, septic systems, they discharge wastewater, even aeration systems discharge wastewater, and that contains a lot of fecal bacteria. And we did a study on that a little while ago, and found that I think it was about 40% of them weren't functioning properly, or more. It was quite a few. And some about 10%, this was like in the early 90s, about 10% of the wastewater systems in houses were basically straight pipes into the sinkholes. So it was things were a lot different back then. Things have changed quite a bit, but they're essentially vectors that go directly into the aquifer, and then people's wells went directly into the aquifer, and they were bringing up things I'll show you in a minute. So this is the way a sinkhole forms. You get the conduit system below, and then the water table. The water table is down here. There's nothing supporting the sediment, and it starts to collapse in, and then this dome-shaped cavity works its way to the surface, and then collapses, and then you get erosion. These things become round. So when you have a sinkhole that's about to appear, so you can have all these stages, and then you can have a piece of grass, you know, like maybe 10 feet diameter, sitting in front of you, that's kind of sagging. Basically, the grass is holding up it's just kind of hanging there like a carpet. And you guys probably remember this, where the golfer fell into the sinkhole. He said, you know, in the interview, he said, well, there was this sagging piece of grass, and I jumped into the middle of it. So there he is in the cave. No, he fell. He's still alive, as I understand. Anyway, big mistake in this area then. So this is what some of the caves look like. I think this is Illinois caverns, and long conduits. There's a stream down below, and then some of them are smaller and filled with water. One of the studies we did was we looked at. I noticed that not all of the sinkholes were the same size. Some were small, some were big, but some were enormous, maybe half a mile long. And what we found was that these look like stream valleys, and they basically are what you're looking at is about 30 feet of sediment sitting on rock with crevices in it, and those that are in the vicinity of large caves. This is a map of Fogopole Cave, or part of it, and you notice that these it extends up here a little bit, but you notice these are really big. These are kind of small in here. The reason is, if you have a crevice and your water is flowing into it, it'll become filled. Say you have a big rainfall, the water will fill that up, and then you'll get a kind of a depositional environment within that sinkhole, so it never really grows. I mean, it forms and it grows, so you see some of these sinkholes with a lot of mud in them after a big rainfall. And those are over crevices. If you're over a big cave, it's like there's an infinite amount of space where this water can gush in and get washed away along the pathway, along the cave conduit system. And so you get more of an erosive environment, so it continues to erode and gets bigger and bigger, and it expands its area of recharge. It becomes a large recharge area for that particular location. So all the water that falls within the vicinity of that sinkhole goes into that crevice or cave. And if it's going into the cave, it'll grow and make larger and larger sinkhole. This is kind of a complex slide. I didn't know if I wanted to show it, but what it does show is, it's fairly easy to explain, is you have areas where there are no sinkholes in the county, and then you approach an area where there's a lot of sinkholes. Basically what's happening is that there's areas called groundwater divides and watersheds, basically, underground watersheds. And so when you're at the boundaries between two watersheds, the water table can actually come up to the surface, or not, to the near surface, and by doing so, it protects, I didn't even touch that. It protects the soil from collapsing. It's called hydrostatic pressure, and it prevents sinkholes from forming. But then once you get that water table below the soil sediment, soil rock interface, this material falls in. You get a lot of sinkhole formation. And so this water flows primarily along the cave system and then discharges to a spring. And so in this area, if you drill your well, you're going to get clean water, but it's going to have probably have a hydrogen sulfide odor because there's a lot of sulfur-bearing minerals within the rock that can actually oxidize during certain conditions and give you that. Give you that reduced sulfur odor. So it's kind of rotten egg odor. The rest of it, this is all oxygenated. So it smells fine, but it could be full of bacteria. In the caves, there's two types of water. This is Illinois caverns. The water's flowing through there. It's probably more dilute, not saturated with calcite. And the water that's sitting in the rocks, coming through slowly, becomes saturated. It has carbon dioxide in it, so acids, and it becomes totally saturated with calcite, which is one of the basically the mineral you're looking at in limestone. And when it enters the cave, the cave is under atmospheric pressure, whereas within the soil zone and in the rock, it's somewhat pressurized so that you can get more and more carbon dioxide dissolved in your water. And when you get into the cave, it's like opening a bottle of carbonated water. Not as dramatic, but essentially the same. And the carbon dioxide comes out of solution. It just kind of bubbles out. And at that point, the water becomes less able to hold any mineral, or most of the mineral content that it had. It becomes more and more basic to the point where it starts precipitating calcite. And that's what's happening here. So you get water moving through the cave that's dissolving the cave, especially if you have a big rainfall event or a flood. You're going to dissolve the walls, make the cave a little bit bigger. You're also going to dissolve the stuff that's precipitating, but in this case, it's precipitating more than it's dissolving. So you get these stalactites and stalagmites. Similarly, I don't know if you've been to Falling Spring, north of here near Dupo, but it's the same thing. It's a small cave, and this water is saturated with calcium carbonate. And when it comes out, it hits the side of the bluff. That's about a 50-foot drop, and the impact agitates the water, and the carbon dioxide comes out even faster. So we found leaves from the fall that are totally encrusted with calcite after a few months. I mean, it's very, very fast. And that's Cliff LaPere standing next to the cliff, and his father was also named Cliff, and they were born at the base of this cliff, which I thought was kind of interesting. Cliff didn't get it. So, anyway, and then this is somewhere along Fountain River. What's the river that goes through there?
Fountain Creek?
Fountain Creek, yeah. I knew it wasn't Fountain River. Anyway, this is Fountain Creek by the Boy Scout camp. And there was a spring coming out of the bluff. Well, it was like 10 foot high area, small bluff. And and it was mostly soil, and the water was coming out constantly. So it was a small spring, and it was so acidic that it wasn't reacting with the limestone before it came out to any great extent. So it dissolved this little canyon. And that thing was like 3 or 4 inches deep, and very interesting. Another thing, if you have a well, or had a well, you notice the hardness of the water being very difficult to deal with. And hardness is measured by calcium and magnesium dissolved in the water, and there's a little formula for it. And basically, you've got dissolved calcite within the water, as you did with caves, and you're getting precipitation of that in your pipes, and it's actually reacting with bacteria, or the bacteria is actually helping to precipitate calcium carbonate within your pipes. So if you have really hard water, often the pipes in your house will get growth rings. So you moved in, you had a couple of kids, and then you're starting to retire, and you try to turn on the sink, and the water backs up, and you think, what the heck is that? My parents had the same problem, and they're in Streeter, Illinois, which is like quite a ways north of here, but they have really hard water. And so when the plumber came, he checked it out. He said, well, there seems to be something in the pipes, and he took the pipe out, and he dropped it because it weighed so much. It was solid. It was absolutely solid. It was like a pinhole going through it. So anyway, so that's scale. Closer to home, well, that's it. This is 3 water samples. When we first came to the area, somebody from north of here, near something like Gibson Lake or something, I can't remember the name of the place. Gilmore Lake, yeah, that was it. Called us and said, we have stuff coming out of our faucet, and when there was a big rainstorm, they had sinkholes in their backyard and all around, and when there was a big rainstorm, they would have mud coming out of their faucet. So a woman turned the faucet on, and mud would come out, and she wanted to know why. And so this is mud, and those are ashes. And what was happening was there were farm fields all around, and there was a lot of erosion, actively eroding sinkholes, and the sinkhole in our backyard, and those sinkholes were all connected to where their well was their well intersected the groundwater, and the well was 200 feet deep. And it was basically open pipe after they got into bedrock. So that was the old way of doing it. And the ashes, we went to the backyard to look at the sinkhole, and after the winter they would take all the fireplace remains and throw them in the sinkhole. And the ashes came out. So anything they threw in that sinkhole went into their water system. Unfortunately, they had their septic system and like 3 other septic systems directed toward that sinkhole. So they could never get clean water from that. After a while, they got formatted this because we wanted to sample their well because it was so interesting, and they didn't think it was interesting anymore. But I understand, I got it. This is a little farther north of Zoo in Wisconsin. They have confined animal feeding operations in a karst area. And during the wintertime, well, every couple of months they apply manure, which they have to get rid of on the fields. And so this, and most of the time it's okay, but in the wintertime they're putting it on ice and snow, and it sits there, and then flows off as kind of a brown foamy liquid, and comes out some of the taps. So this is basically their water. That's an instrument we're measuring some parameters in, but the suds and the brownish water is basically material they were putting on the ice and snow, and we call it tea up there because it sort of looks like tea. So this is LIDAR, and it's basically it's an acronym for light detection and ranging, which doesn't really tell you a whole lot, but it's basically is what I told you before. It's an array of lasers in a plane that comes down and paints the ground surface elevation. So somewhat like this. The plane's usually not that low, and they try to do it at night and when there are no leaves on the trees, because they can get through the trees like that. And then the first returns, they'll hit something high, and then the light will come back first, and then the last returns come from the ground. So they could separate these and get scrub away all the vegetation. So this is kind of like what it does, and so when you get a representation of the laser returns, you get the red is the first stuff you get back, and then yellow, and then eventually the blue is the last returns, and you can actually determine where you clip off the data, and then you just see the bare ground. So we looked at, this is Southwestern Illinois, and you can see these dark areas. There's sinkholes, and this is from aerial photography by the Department of Agriculture. And this is the same thing in LIDAR, same area. Now, so if you see a couple of sinkholes here, and then you see a depression here. So it's not real dramatic, but if you scrub away the trees, and this will be the same image. So if you focus on something like that, I screwed it up. Okay, there it is. Anyway, the trees are gone, and you see that the sinkholes are much fresher, not so, and you had an agricultural field, so they're plowing these things over and over and smoothing them out. So with the areas with the trees, you see much more detail than you normally would, unless you walked around on the ground. So that's another example. And what we did was, initially when we came down here, we took USGS topographic maps and counted sinkholes and said, okay, 1, 2, 3, it's low tech, but it was a way of getting at how many, sinkhole density is what we're trying to get at, and look at relationships of sinkhole density with groundwater contamination. So you see some of the stuff under the trees. You can actually, they got some of it, but with the using the LIDAR, you see much more detail. And this is more like a 10 to 20 foot contour intervals here. Here you can get 5 or 2 foot contour intervals. Basically, you can figure out exactly what's going on the surface as far as erosion. This is a little sinkhole that recently formed in somebody's backyard. So it's much more detailed. We also looked at air photos from 1940 and 2005, and as well as LiDAR, and tried to combine all of this. In the 1940s, you're right at the tail end of the Dust Bowl era, and so what happens is the sinkholes had kind of a rim around them, a very dry area around them, and they stood out. This is 2005, and then we peel that back, and then you can see 1940, and you can see the white areas. So they're much more enhanced. So we could look at that, and then with LiDAR compare what the looking at the same sinkholes, and we found like 30%, a third more sinkholes with LiDAR, and with the aerial photography we found like 10 or 15 more. I think it was 15% more and 30% more with LiDAR. So we're starting to look at this area in detail using LiDAR. Okay, this is, we're going to switch to the earthquake stuff that we found. We were going through the caves, and I noticed let's talk about earthquakes first. The New Madrid seismic zone, you hear about the earthquakes over in the West Coast, but the New Madrid seismic zone was the area of a massive series of earthquakes, or a series of massive earthquakes, back in 1811 and 1812. It was like December of 1811, and it lasted for like 6 months. And people experienced magnitude 8. There was 3 magnitude 8 earthquakes in this area, in this red area. And then as you get farther away, the magnitude decreased. But massive earthquakes. The Mississippi River actually changed course. It went back to the north, and and boats were thrown up on the shore. I mean, bluffs started to collapse into the river. It was fairly intense, and then parts, there would get crevices that would open up, and methane gas would be exposed, and then the rocks are banging into each other, and it creates sparks. So flames would come out of the ground occasionally. So people thought it was the end of the world at that time, and this is the New Madrid seismic zone. There's also a Wabash Valley seismic zone to the northeast. So these are areas where the periodicity of the huge earthquakes is like every 300 to 500 years, and it goes back to the data go back to maybe 10,000 or so years, 20,000 years at the most. And so there's a lot of research on this. People have been looking at earthquake events or seismic events where they can actually pinpoint the epicenters. And so you're down at the boot heel of Missouri, there's Illinois, and so the epicenters tend to occur along fault plains. So there are like 3 or 4 faults involved down there in an area called the Mississippi Embayment. And what's happening is these faults are moving, and one moves and they're all connected, and then another one moves and another moves. So you can get repeated earthquakes, and so the 3 major earthquakes they got are probably related to movement of these 3 different faults in that area. As looking underground, You see, it's called the Mississippi Embayment, and it's a kind of a depression just south of Illinois that, and it's subsiding, or it was subsiding. It's still active, and so it's filled with sediments from the Mississippi River. What happened was there were igneous intrusions. Molten rock would come up into these fractures. The stuff was mobile. The crust of the earth in that area was actively splitting apart the continent, and it stopped. But this is what's left over. So with the December 1811 earthquake of magnitude 7.2, it was felt in Boston, and I believe it rang the church bells in Boston. So it was that widespread. People started to move after a while. One of the ways that we're able to trace how long ago these occurred, looking at the periodicity, how often, and the magnitude actually, is something called sand blows or liquefaction features. And so we're seeing piles of sand in this field from an earthquake. And there's a close-up of one. And what happens is that the ground fractures and everything's shaking, and the sand deposits at depth become liquid, and they squirt up these fractures and then shoot out on the ground like a geyser. And it's similar to a ketchup bottle. If you have to hit it to get the ketchup out, it's solid, and then you start vibrating it, and it turns into a liquid and flows out. And that's essentially what's going on. But what's nice is the sand covers over vegetation, and then when you dig these things up, you find the soil horizon, and so one of the episodes, or one of the earthquakes, occurred here and here, and you find carbon based material, old vegetation, and you can date that with carbon-14 dating techniques, and go back quite a ways, 40,000 years, 50,000 years roughly. But you can date when this earthquake occurred, because the sand is lying on top of that sediment or that carbon-based vegetation. So this is the way we've gotten the information that it's been about every 300 to 500 years we see these earthquakes. And this is just a summary of what I just said. So basically it comes up, and then it's datable. So when we were in Fogable Cave in Illinois Caverns, this is Fogable Cave, we saw features like this. So this I thought was kind of interesting, because it was basically the only living witness to the 1811-12 earthquakes. These white stalagmites that look like bumps on the head were initiated by the earthquakes. And what happens is that the rocks have tiny fractures in them, and they move around. And so they can dilate, or they can open up a little bit when you have these vibrations going, or seismic waves moving through the rocks. And it opens them up just enough where they start dripping. The water can start dripping through there, dissolving, and it's soil water, and it's dissolving the calcium carbonate and forming these little white stalagmites. So we saw these, and they're all the same. There's one, some of them look like icing on a stalagmite. You get a brown stalagmite with a little icing on it, or a little calcium carbonate. And we dated these using uranium thorium techniques. The water going through the soil zone can dissolve uranium, which is basically everywhere. And it's in minerals like feldspar. And so you have sediment with uranium-bearing minerals, not much, and they dissolve, and then it carries the uranium down, and then it drips and forms stalagmites, and then you can take the stalagmite, and after it precipitates, after you get calcium carbonate, the uranium decays into thorium. So you can look at the uranium-thorium ratio and get a date for when this all started, and these are all about 200 years old. And we see them in Missouri, and this is a feature called the wine table, and you can see these little white stalagmites, and they're a little off-center, and because of the movement of the fracture. And so here we are, and what we try to do is drill into these things to get our samples so we don't disturb the stalagmites, and then we fill them in. Occasionally we collect a sample, and so you can see the white draping over here, and it's not dead center, it's a little bit off center. And so by doing this, by looking at these rocks, or these stalagmites, we're able to, we found dates for earthquakes using this that match the stuff in the liquefaction features of the sand blows, going back, our stuff goes back over 20,000 years. So we have about 40 different dates that we're looking at that seem to be related to earthquakes, as opposed to with the sand blows, there are only maybe a dozen dates. So it's a lot more efficient as far as finding earthquake dates, but with the sand blows, you're able to look at magnitude of quakes, and with this, we haven't figured that out. So right now, I'm working with a guy from the U.S. Geological Survey in Menlo Park, California, and so late August, we're going to go to a cave in southern Indiana called Marengo Cave, and I think Focal Pole Cave, and Round Springs Caverns in Missouri, and he's looking at stalactites, and the stalactites tend to fall during an earthquake if they're long, like the little soda straws, and they start to pendulum, and then they collapse, and it gives you actually if the seismic wave is moving in this direction, they'll pendulum in this direction toward it and away from it, and then fall. So they're all lined up. So in Marengo Cave, we saw, I didn't bring a picture of it, I wish I had, a lot of stalactites just lined up. So we're going to combine the two techniques and try to make it more usable as a technique for identifying earthquakes and looking at magnitudes of quakes, because the greater the magnitude of the quake, the more prone you are to knock these things, the stalactites down. So we found in Marengo Cave both the white stalagmites and the stalactites. Now this is one of the this is a stalagmite we found we collected in southern Indiana, and it was a pair of stalactites right next to each other, and we started one on actually this is reversed, so this one started growing, which is this side, about 280,000 years ago, and this is all uranium thorium dates, and then it progressed to about 170,000 years, and it stopped growing, and then it switched over to the base and started growing here, and about 100,000 years ago it stopped growing, and the stalagmite sat there for about 100,000 years, and then 6,000 years ago both sides started growing again, and right at 6,000 years. So we looked at the sand blow data, and it was the cave was located here, and this is an area where the sand blows were all dated. You're using carbon-14 at 6,100 years, plus or minus 200 years. So it's not exact, but it's pretty close. So about 6,000 years ago, there was a major earthquake associated with the Wabash Valley seismic zone, and so we picked that up in this pair. So, and I think this is the last thing. So if you're dying here, you'd be glad to know this is all I'm going to talk about. One of the things I always want to do as I went through the state, I found salt springs, saline springs, you know, and the Illinois basin is full of salt water at depth. So the deeper you go, the more salty it gets. And so when you get down to the bottom of this pile of sedimentary rocks, the brines in there are concentrated to the point where they're almost saturated with sodium chloride. And so you get like 300,000 milligrams per liter, which is like 30% dissolved sodium chloride, which is, you know, and then you get to the point where you almost can't dissolve any more sodium chloride. And as you come up, as you get shallower, the brines are more dilute, but they're still brines. And so what you have is a freshwater lens sitting on all of this, and there's water coming in from the sides of the basin, but you know, fresh water. But for the most part, it's the freshwater lens, and occasionally you come across a spring where you have a structure like a fault or a fold, and the rocks are disturbed in some way, and this deeper water is coming up, and there's probably 50 or 60 of these things around Illinois, and I've seen several of them, so I finally got some money to do a study on this. And what we found was, it was very interesting. These things go way back historically and prehistorically. We went to a place in Kentucky where, let's see, it was called Big Bone Lick, and it was a Pleistocene boneyard, and Lewis and Clark came across it on the way across to the West Coast, and it's basically, you have these muds from the brines coming up, and they're kind of a black mud, and the large mammals would tramp around there licking the salt because they, you know, everything, all these herbivores, planting animals have to have salt, a source of salt, so they were licking or drinking this water, and they get stuck in it. It was kind of like the La Brea tar pits of the Midwest, and they die, and then things would jump on them and eat them, and then get stuck. Anyway, so we were there, and there's still a lot there. The Native Americans also noticed that the animals came to lick the salt, so they would use these as hunting grounds, and occasionally they would collect the brine coming up, put it in pottery, let it evaporate, put some more in, and at some point smash the pot and collect the salt, crush it up, and use it for preserving meat and preventing infection. You know, they put it on a wound and seasoning. So the first settlers came in, and the Native Americans helped them find these salt sources because they didn't have any salt, and they were having problems without it. And eventually the settlers took over the spot and used it for hunting ground, and then took it over as a means of making salt that they could actually make money on by selling it to the people in the area. And they would get a couple dollars a pound for this, and it was big money back in the 1700s. And they used, they had these big iron kettles. They weighed about 400 pounds each, and they'd fill them with brine from the spring. And then they'd build kind of a trough and put wood in it. They'd clear cut the area, totally get rid of all the wood for fuel, and then have a chimney, and then they create a draft that would go that way, and then, heat up all these, get these things boiling. And this is a recreation of one. And it's interesting, you have to, as this brine boils, it precipitates the salt in a crust on the surface, and then that sinks, and then another one forms because all the evaporation is occurring to the surface. So you have to take a scoop and scoop it out of the bottom, and then put it on a drying table. Otherwise, you will get a solid block of salt in your iron kettle that you cannot get out. It's really hard. So, and so here, this guy is, this is a pottery that was evaporated, and formed the salt cake that was smashed, and that's one of the kettles that he was using. This is a site in southern, just south of Louisville, Kentucky, called Bullets Lick. And so here are the rocks that they used for the chimneys and to support the kettles. And you could, and the springs, they actually found the spring, and then they drilled a small hole, dug a small hole, and collected the water in that way. So it's kind of like a little well. So we went there, and you notice everything is dead in the area. Just beyond this is something called Phragmites. It's vegetation that grows like this. And so this gentleman that owns property cut a hole through it because you can't get through it. You cannot walk through it. It's impossible. So I didn't think that was something you couldn't do, but I tried. So he cut his way through there, and the Phragmites is salt loving, so it grows where there's a lot of salt in the groundwater. So we got there, and we dug a hole and hit the brine that the settlers were collecting back in the 17 and 1800s, and we analyzed it. Pardon me?
How deep was it?
Oh, we went down 4 feet and we hit it. Pardon me?
That's all.
That's it. It was actually on the surface. It was kind of oozing up on the surface, but not enough for our samples. And plus that had been evaporated. So we wanted to dig for some fresh stuff. And so it was, 4 feet, and then we started getting it. If we'd gone a little deeper, we would have gotten a lot more than we did, but we had enough for our samples. And so if you lick the rocks, you could taste the salt. You would want to lick them. After the bottom fell out of the salt business, which was about mid-1800s, 1850, the people would go to these springs and drink the water, and and it was medicine was not where it is today. So anything that had an effect was a medicinal cure, and so this actually had some effect. I mean, if you bathed in it, you could actually kill bacteria on your skin or infections and that sort of thing. So it did have an effect. So this is at I think Big Bone Lake State Park, and so we're just collecting some samples here. But people would come with their families or their wives and collect the water and drink it. And this is West Baden Springs Hotel in Indiana, southern Indiana, and from 1855 till now they have this they have Pluto water, which is basically salty water. with a little hydrogen sulfide added for flavoring. And people came here a lot of people came here, rich people, and they come in on the trains and they'd spend the summer here and they would drink the water and it would have a laxative effect. And also it had lithium in it, a lot of lithium. So lithium is a psychoactive element and it makes you feel better. So they would drink, what they would do is they'd go to the spring. This is kind of a little gazebo thing around the spring. They'd go drink the water and they'd drink as much as they could, and then they'd go for a walk. And they had outhouses every so often along these paths. And so they'd go for a walk. And then, so by the end of the day, they were really hungry and they felt really good because of the lithium. And then they would drink. You know, they had a lot of wine and food. And they would pack all of their clothes and so it was a big fashion thing too. So yeah, so that was pretty nice. They also sold this stuff up until they found out there was lithium in it, and then the US EPA said, no, you can't do that. So, and then these are just areas where the blue circles are the points where we sampled. Big Bone Lick is actually over here. Bullets Lick's down here. Southwestern Illinois is here. And then, if you've heard of Salt Lick Point near Velmeyer, that was a place where apparently they collected salt. We visited there. Actually found the area where we could get a sample. Excuse me. Found an area where we could get a water sample that was salty, and then salty enough to do our analyses. So we sampled this, and then another area was near Columbia, the southwest of Columbia, Illinois. And so it was along a stream. The stream is over here, and that was a depression in the ground. It was when salt water interacts with fresh water in the carbonate rock and limestone, it makes the mixed water much more aggressive, and it dissolves the limestone very fast. So this was like 10 feet long, 5 feet wide, about 3 feet deep, and it was totally covered in iron sulfide, so it's black. So it has this black coating everywhere. And then this bacteria, it's a bacteria that it's white and filamentous, and it looks like hair. And so you can see it, kind of like there. And it's very impressive. You get there and you see this, and the stream bed becomes black. And then, that's, and the the limestone's all dissolving. And then you see this white stuff, and it looks like white witch hair, and it's about that long, and it's kind of waving in the stream, and it's very cool. So, and anyway, so we're finishing up that study now. And I couldn't resist this.
Elvis was a geologist too. Wow.
Anyway, thank you very much. I'll take any questions you might have. Yes, sir.
I'm interested in trying to find maybe a total map or something, or some type of photograph of the ground that I live on, and see what it looked like before the home was built. Is there somewhere that we can do that?
Yes. If you give me your name, I could put you in touch with the people at the survey that can tell you that. There's aerial photography. Aerial photographs go back to 1940 in this all over Illinois, and so you can I don't know, when was it built?
93.
Oh yeah, well, Yeah, it's, yeah, you can get that. And it's all available. So I could give me your name and address, I could get in touch with somebody.
How far down, when you guys have, I mean, you've probably done core samples to go down deep enough to get into the salt layer where it's 300,000 parts per million, right?
Yeah, it's not exactly a salt layer, it's just a brine.
Brine layer?
Right.
What kind of bacteria do you find in there? Is there anything, I mean, can anything live in that?
Yeah, there's a halotrophic bacteria. I can't remember the names, but halotrophic means halides or sodium or chloride and bromide and all that. And these organisms love that. It's probably an archaea type bacteria, really primitive, and that's kind of stuff that lives there. We're seeing that coming up in some of these springs.
How far down do you have to go to get that?
Well, there's a borehole that the Geological Survey drilled in 2011 to the bottom of the rock pile, the sedimentary rock pile, and that was 1.5 miles. And that was in Decatur, Illinois. In this area, it would be a lot shallower because you're at the margins of the basin, so the basins are coming up. So maybe, I don't know, a couple thousand feet if you get the right spot around the Mississippi River. So, yes?
You had some slides, you had a slide before showing the sinkholes in this area.
Right.
Where's the Dupo anticline in relation to those sinkholes?
It's in the area of Dupo. I could probably bring it up.
I mean, yeah, on that slide was the...
It was, it's roughly north-south trending, drawn line in the upper left of that figure.
You can see it on the bluffs there if you.
Yeah, Sugarloaf Hill.
Yeah,
Right.
right
And
there
then-
behind the guy that's got the boat repair place. You can see there's an anticline there.
Oh, really?
Don't the oil wells and stuff follow that?
That's right,
So
yeah.
back on F Road, where the oil is, behind Walmart in that area back in there. So that gives you an idea from Dupo down behind Walmart, sort of.
Okay.
Yep.
Yeah, so, yeah, the anticlines act as a trap, as you're right, exactly. And the oil is migrated through these rocks and entered places where, for example, if there's a layer of shale, which is usually fairly tough to move anything through, the oil being lighter than the water, it would tend to migrate into these traps, and that's where they're punching in and getting the soil. So, yes.
Okay, two questions. One, how's the water quality in the county since the early 90s when they had the groundwater education group, and then they started getting fountain water? And then two, I've heard that Monroe County is the holiest place in the United States. I have no idea if that's true or not. Not religious. Yeah, not religious. Yeah, sinkholiest, I should say. Not distracting from those people who are the other, but where would I have heard that? Is there any evidence to that, or did somebody just make it up and look at find it?
It's one of those. It's one of the holiest places on Earth, basically. But,
On Earth?
sure.
Okay.
Yeah, a lot of holes.
That's
But I
great.
mean, you go down to, you follow the rock, St. Louis limestone down to Mammoth Cave area. A lot of sinkholes down there, a lot of caves. Caves are bigger, longer. Mammoth Cave is 350 or so miles long so far. And there's a lot of other caves. So, there's a lot of
Somebody told
openings
me-
here, but yeah.
Yeah, New Hanover, there's a section out there, a square mile, that supposedly is,
Well, we looked at sinkhole density, and you see maybe 100 sinkholes per square mile. or more. And they're big, I mean, they're not like sinkholes, I mean, this is like 300 feet in diameter. And at some point, we realized that actually the whole area is subsiding while it's eroding, so you're getting a major depression, you know. And so even though you're on what appears to be the ridge of between two sinkholes, that's eroding too. So it's kind of a general. This is like around Fogelpole Cave. I mean, it's a lot of collapse in the area. And then you can get sinkholes within the sinkholes. You know, it's like. So at what point you just say, well, you know, got more sinkholes and there. So it's hard to say, but you have a lot, and it's one of the most sinkhole-rich areas I've seen anywhere. So, sure. Any other questions?
I mentioned that.
Oh, this.
Yeah.
Yeah.
Yeah, we can.
Okay. This, I think, was emailed to everybody?
No, just ours.
Okay, it hasn't been emailed to you, but it will be, right?
Only if you leave your email.
And basically, it's a summary of, I have to take a quick look, see what it was. Summary of a lot of the work we've done in this area. It's a field trip guidebook that we did for a trip of the Sinkhole Conference, which was in St. Louis, Missouri in 2011. And we led a field trip down here. And it gives you the highlights of the karst and water quality and that sort of thing. So, and you get it for free if you drop off your email.
Right.
If you're not already on the past email.
If you're on our email list, just let us know.
Just add your name and email to the sheet of paper we had out front.
And we'll send it to you for free. Any other questions? Okay, thank you very much.
Okay, thank you very much.